Okay, somehow not so. Oh, I think it's okay. So, hello. So I will talk about some, the execution model for CPUs. Actually, not yet for GPUs. So I'm really interested in to look into GPUs, what's going on, and then understanding, and somehow there's a way to develop higher level, simpler models. But I actually, yeah, it's interesting to hear that I knew that load buffering happens in GPU, but somehow it's important for performance reasons. So I really want to look into it. But anyway, my talk is only about CPUs. Okay. So and for CPUs, I think we figured out that simple model can be possible. So the subtitle is that RC11 is good enough without performance overhead. It's actually same line as Stefan this morning gave talk, and then it's basically same direction. And so first, weak memory behaviors can be caused by many compiler optimization, hardware optimizations, but I think they can be captured at high level by 4 kinds of reorderings: load, and read, write, and write, and read-write reordering. That's called load buffering, right? And then there are many weak memory models, and among that, there are some models. The models itself are out of order. So in the models, your instructions can be executed out of order, right? So C11 is like that, and then promising semantics is also out of order. And here, but for promising semantics, and then these models captures all 4 reorderings in a correct way, okay? So, and then in the promising semantics, I want to say one thing. So the promising semantics has 2 mechanisms, view and then promise. And view does not change the execution order. Still, the instructions are executed in program order, but it only relaxes the state of memory. So memory now contains a set of messages returned to the location, and then with some partial order things. The memory itself is relaxed, but execution order is still in order. Okay, and then so this view mechanism can model read, reordering, read, and write reorderings. But for load buffering, the read, write reorderings, we really need a mechanism that execute instructions in out of order. So that's called the promise. Okay. And then, so these models are efficient in a sense that the program can be efficiently compiled down to hardware for sound compilations. And then, but downside is that it's quite complex. It's very complex because the instructions can be executed out of order. So reasoning about the programs is hard, and it's not easy to develop good reasoning principles. So for example, I have a code, and there is my code, and then there is a caller. You don't know the code of your caller, right? But your caller's code may be executed during your execution. So you're executing your code in the middle. Some caller's unknown code may be executed out of order, right? So this complicates your reasoning, and it's a very, complex model. Whereas there's in-order models. Okay, so for example, RC11 repair the C11, and then also promising semantics without promise, just with the view, okay? Without promising mechanisms, that's now in-order semantics, because view does not have out-of-order execution, okay? So, and then these models can capture 3 reorderings, but not load buffering, okay? So the upside is that it's simple. It's just in-order interleaving execution. So it's not so hard to develop reasoning principles. So for example, there is a logic called the compass that's sound the logic on top of this simple model, the in-order models. And also, you don't need to worry about any kind of out of thin air or semantic dependency and so on. Because by construction, there is no out of thin air. Okay, it's a simple model. But on the other hand, it's in some sense inefficient, because some performance overhead for sound compilations. For example, for RC11, certain load introduction optimizations are invalid, which may well be performed by compilers. And also, certain read-write load buffering reorderings performed by hardware are invalidated. Okay, so we have to pay some performance overhead. Okay, but we had some result, positive result, and saying that actually RC11 is good enough. So the performance overhead we considered in the previous slide, the two things, they can be lifted. So we figured out how to lift the performance overhead for RC11. So what I'm saying is that you can use RC11 as a C semantics as a source. There is no performance overhead to pay. Okay, and then we formalize all this work, and then for this we define the operational version of RC11. So RC11 is axiomatic, and we define the operational version, which is essentially same as RC11, but it's slightly stronger than RC11. It has fewer behaviors. And it's basically based on view mechanism. That's why VRC11, view-based RC11. And then that's a promising semantics without promise. It means that only view mechanism. And then plus catchifier mechanism on race in non-atomic excesses. And then in order to detect race on non-atomics in operational and also in other way, we defined a very simple detection mechanism. So it's different from RC11's race detection. So we trigger fewer catchifier on race. So we allow more races than RC11. So this is stronger semantics than RC11. So if this is good enough, RC11 is also good enough because it allows more behaviors. Okay, and we proved every result in Coq with respect to VRC11, which is stronger than RC11. Okay, but just one thing is that we support SC fence, but not SC read and write yet, because SC read and writes are quite complex, and so that's a future work. Okay. Other than that, we include all other atomics. Okay. Okay. So that's the introduction, and so I will discuss problems with the in-order executions, the performance problem, and then how we lift the performance overhead. Okay. So just let me check the time. Okay. So the IC11 or VIC11 has two access mode, non-atomics and atomics, right? And both are in order. So in IC11, so they are executed in order. Okay, but non-atomics, there is a race. It's a race-free. There is a catchifier. So if there is any race detected, then the semantics become undefined behavior. Okay, and then this non-atomics is mapped down to hardware, and atomic accesses are also mapped down to hardware. Okay, and then the problem here is that since this is in order and catchifier, we have some issue with the load introduction. First, usually the in-order execution do not allow read-write reordering optimization, but thanks to catchifier, any race on non-atomics as UB, undefined behavior, we can allow read-write reordering. Okay, but on the other hand, load introduction becomes invalid in this model, because if you introduce a load, it may introduce race, right? So it may introduce UB. So this is unsound. And this is a problem one. Okay, this is a problem because we want to allow load introduction. And the second, for atomics, since we do not have catchifier, read-write reordering is unsound. But we do not view this as another problem, because of the same reason as Stefan talked in the morning. And so actually I misunderstood his argument. So he does not want to allow read-write load buffering reordering for atomics, which we also agree. Okay, so the reason is because the compiler should not optimize atomic accesses, because in order to understand the atomics, you have to understand the other threads code as well, because atomics means that multiple threads act at the same time. So just looking at one thread's code, and then you cannot understand the intention of the atomics. Whereas non-atomics is that only one thread is accessing it. So by looking at the thread code and optimizing, it makes sense. So we want to fully allow all optimizations on non-atomics, but we don't much care about optimizing atomic itself. But optimizing non-atomics across atomics we should care. So we fully support those things. But we just don't care about optimizing atomic instruction itself. Okay, so even though this is not allowed, we think it's okay. And actually also LLVM and GCC, as far as I know, they do not do this kind of reordering for relaxed writes. Okay, so this is not a problem. But finally now, the atomics has an in-order execution model, but whereas hardware has out-of-order execution model. So this mapping from atomic relaxed write down to plain store is unsound because the hardware may reorder it, right? So in order to prevent reordering performed by hardware, one way is to insert fake branches after every relaxed load, okay? So that the relaxed load and then previous preceding writes are not reordered in the hardware. So there is a performance overhead here, right? So Stefan said in the worst case, like a 6-point-some% overhead, right? So I think that's important to non-negligible overhead. So this is a problem.
That did average out to 0.
Sorry?
It was some were getting, in the paper that I read, some were getting 6% worse, some were getting 6% better. The average overhead was 0.
Ah, okay. But still, there is anyway some impact, right? So if we can eliminate it, that might be good. But anyway, so that's arguable. But anyway, so we view it as a problem, and then if there is nice solution, that's good, right? So anyway, we are dealing with these two problems, okay? Okay. So and then so is that clear? So I will show you the solution. Solutions are somehow not very technical. Some parts are technical, but anyway, so our solution is that first, instead of using RC11 as compiler IR semantics, we differentiate source language and compiler IR semantics. So in the source semantics, we use in order RC11, but in the compiler IR, we relax. So we use promising semantics on non-atomics, and then in order semantics for atomics. So atomics is the same for source and then IR, between source and IR, but non-atomic semantics are different. In the source, it's a catchifier in order, but in IR, it's a promising semantics on non-atomics. Okay, so this is stronger model than this. Then what happens is that in this promising IR model, all the optimizations are sound. So we formally proved in core, and also we proved that the non-atomic catchifier in order semantics is weaker than this promising semantics. Okay. So this problem is solved. And second, this one is not problem. We consider it as no problem, so we just keep it the same. And the final problem, the mapping from atomic to hardware. So previously we inserted fake branches after every relaxed load, but now what we are saying is that insert load store fence before every relaxed write. And you may say this sounds strange, but somehow we claim that this is okay, this is good, 0 performance overhead. That's our claim. And then why, right? And also there is no load store fence in ARM, right? But we are claiming this. So it's a funny thing. But I will explain why we are claiming this way, okay? So I want to tell you some observations on load buffering or read-write reordering in hardware, okay? So first, if we do not allow load buffering in hardware, what happens? Okay, the impact of restricting load store reordering. So let's talk about that. So first, these 3 reorderings are very crucial for hardware performance. So this happens, I think, basically most of CPUs. Okay, and then but load store somehow, if you try to observe it, very few CPUs you can observe. So for example, in power, there's never this load store reordering has been never observed in any power implementation, and then also very few old CPUs you can observe. But since 2016, I think no one has observed load store reordering. And also I heard that from ARM's internal document, the ARM Cortex officially do not allow load store reordering by design. Okay, so. And this is rare. So then the question is why it's rare. And then, so I talked to hardware guys and then understood that these 3 optimizations are very significant, but load store optimization, rewriting optimization is kind of for CPUs. It's kind of very small benefits. So it's kind of not important. Okay, so I talked to some internal guy in ARM, and also I talked to several hardware guys, and then they were actually surprised that this load store reordering is visible in hardware. So they basically, hardware people think that it's not visible in hardware implementations. And then this guy from ARM said that he cannot believe that actually load store reordering is observable in hardware. So I showed him some data, and he said, oh, this is very surprising. And then, but the data is only very like 10 years ago data. And then anyway, these guys think that load store reordering is useless for CPUs. Okay. And then, so I ask questions, and then let me tell you my intuition. This is my intuition why load store reordering is useless in hardware implementations. Okay. So let's look at the CPU core, a CPU core, and then there is a load and store, right? So you may this load may take some time because, for example, cache miss kind of thing, right? Then what happens is that the CPU execute further y equal 1, and then even during even when this is incomplete, y equal 1 is executed and it is put into store buffer, okay? And at this point, inside of the CPU, once this store is sent to store buffer, it is considered as completed. So you can keep execute the later code, okay? Even though the load is not completed, but you can finish this store. So inside of core, load store reordering happens. So incomplete load does not prevent executing further instructions, okay? So internally, inside of core, it happens, but externally, it's not observable. So that's the point. So internally, the CPU in-core optimizations are all done, okay? Let's keep executing. But the point is that when this y equal 1 is flushed to cache so that other cores can see it, right? So there is two choices. You wait until these preceding loads are all completed and then flush it, or you just flush it before this is completed, right? There are two choices, right? So forbid commit before the load completion or allow commit before the load completion, right? And then if you forbid it, so you commit it only after all the loads are done, preceding loads are done. Then the load store reordering is invisible to other cores. So you cannot observe any load store reorderings because it's just the load store reordering happens inside of single core and it's not visible to others. So load store reordering is invisible, okay? But if you allow commits, okay, and then this is what most of CPUs does, because anyway, the in-core optimization is important for them. So there is no kind of basically downside for doing this. So that's why most CPUs do that. But on the other hand, if you allow it, okay, then it's visible to other cores, and then the load store reordering is observable. But there is a downside because CPU design becomes kind of more complex, and then so there is a more specific reason, but okay, I will skip. But anyway, there is a cost to pay for this allowing this complex commit, right? Just if you commit it after load is done, that's a simple. But if you want to allow commit earlier, then many things you have to consider. So it's more complex, and then also the in-core performance benefit is that only when the buffer is full. If the buffer is full, you can kick out some write more quickly, and then you can execute further instructions. So the in-core performance benefit is only when buffer is full, and these days the buffer is kind of big enough for most of performant CPUs, so they don't care much about this. So maybe for some special CPUs where buffer is very small, then you may consider committing this store earlier before the load completion. Okay, but anyway, so this is why most of cases you choose the first one. Okay. Okay. So anyway, so this is the reality, and then our solution for efficient mapping. Let me see. Okay. So how much time I used?
You've got about 3 minutes left.
Oh, okay, okay. Then I will stop here. So, okay, so solution for efficient mapping is that we propose RW load store fence in ARM, which is basically no op for most cases, and the very few old CPUs, they may have some small performance overhead. And then with the RW fence, it's easy. We just put RW fence, which is no op basically by definition. And then without RW fence, we can use just plain store for most CPUs, and then few ARM CPUs, we use a store release. That's a current kind of tentative solution. And that's all. And then, but finally, so this is our picture, and we have one more big picture. So for compiler, so this is a simple model for programmers, that's good. But for compiler writers, this is complex model. Promising semantics is complex. So what we did is that we provide sequential model, even not concurrent one, just a simple single-threaded sequential model. And then we proved that every non-atomic optimization sound on this single sequential model is also sound in promising model. That's what we formally proved. So compiler writers just need to think about even simpler model. So for programmers, in order execution, for compiler writers, sequential model. Okay, that's all. So thank you.
We have time for exactly one question. You were very fast, so.
Yeah.
So, Gil, I really do have to interject one thing, which is that you talked to hardware designers and said, and they said to you that they're surprised it happens. Then you prove them wrong with some data, and you still believe them that it doesn't happen. It's not that 10 years ago, the data is not from 10 years ago it happens, and then the data from today it doesn't. We just don't have data from today. Nobody's doing systematic testing of hardware to check for these things, and you shouldn't believe what hardware people tell you about their hardware.
Yeah, but at least, okay. But anyway, that's what hardware people think. And then also the ARM's internal, at least Cortex do not have that one. And then also we tested some the MM CPUs, and then we didn't find any load buffering on the Apple CPU. Okay.
Very skeptical.
Okay, they're still setting up, so let me just. Peter's had his hand up, so I'm going to go to Peter first. Yeah.
Okay.
So just as an empirical point, historically, if one, I've tested this several times, if one goes to ARM and says, hey, why don't you strengthen your architecture to forbid this LB that you don't do very much, they say no. I tried it.
Yeah, because maybe the backward compatibility or so. So my proposal is just to propose a load store fence. So if the architecture do not allow LB, that's no op. If it allows LB, then it's not no op. It does something.
I'm not saying it's a bad idea. I'm merely saying that so far they have always said no.
Okay. Yeah. Okay.
Okay, thank you.
Okay, thank
We'll
you.
stop
Thank
there,
you.
I think.
Yeah.
Yeah, thank you.
Yeah. Okay.